Section 2. Okay, in Section 1 we talked about some subjective properties of distributions, shape mostly, and various properties of the shape, things that you can see by eye. In Section 2 we want to talk about some things you can compute from a set of numbers, some actually objective measures that describe quantitative data. In particular, the idea of centers and spreads. So we want numbers that we can compute from a set of numbers, say everybody's heights or everybody's grades. We want numbers that we can compute that represent the center of the distribution, and numbers that we can compute that represent how spread out the distribution is. So, if this distribution is symmetric, for instance, something like this, then there is no doubt about what we mean by the center of the distribution, right? We've talked about that in the last section. Symmetry is a difficult concept, but if something is symmetric, then you know where the center is, and if you know where the center is, you can tell whether it's symmetric. It's a kind of a chicken and the egg thing, but symmetry, we know what we mean by symmetry, and if something is symmetric, then regardless of the shape, whether it's like this or whether it's rectangular or maybe there's a big valley in the middle, there's all kinds of ways it could be symmetric. But if something is symmetric, then it's pretty clear-cut what we know what the center is. What you have to understand is that center and spread are not technical terms. There are different things we could mean by center, and there are different things we could mean by spread. So let's start there. What are the essential characteristics of anything that we could call the center of a set of numbers or the center of a histogram? Well, first of all, if it is symmetric, then it better be in the obvious place. So if you have a symmetric distribution like this, then whatever number this is on the scale, that better be the center. Now, if the distribution is not symmetric, then there's some room to maneuver on what exactly we mean by center, but the minimum requirement is that it should be in the obvious place if it's symmetric. So we have an idea of what we're talking about when it comes to center, but there is room to maneuver. What about spread? Well, I didn't plan ahead with a nice picture for this, but we had some nice ones in the previous section, you may remember, of distributions that were centered in the same place but had different spreads, and we were just doing that visually. It was clear that the taller, thinner one was less spread out, and the other one was more spread out. And you can call up those pictures in the notes online. But what are the minimum requirements of anything that we could call the spread of a set of numbers? Well, first off, spread is a non-negative concept, right? We'll talk about what a spread of 0 might mean, but clearly if the spread is smaller, if the number is closer to 0, then it is more bunched up, and if less spread. And if the number is large, a big positive number, then there is a lot of spread, so more spread out. So that is the minimum requirement of anything we could call the spread of a set of numbers. But again, they're not technical terms. There's different things you can mean by center, and there's different things you can mean by spread. We're going to talk about the two major types of analysis that you can do on a set of numbers. On the one hand, you can do a type of analysis based on how the numbers balance out. And that's going to have its own notion of center and its own notion of spread. On the other hand, you can do a form of analysis that has to do with where things fall in an ordered list. And that form of analysis will have its own notion of center and spread. So loosely speaking, we've got the order, we've got the balance scheme, and we've got the order scheme. We can do an analysis of the numbers based on how they balance, or we can do an analysis of the numbers based on where they fall in an ordered list. But again, in either case, the thing that we call the center should be in the obvious place if it's symmetric. It's only when it's asymmetric that there is some room to maneuver. The center could mean different things. So I didn't really summarize it in one place here, But in the balance scheme of things, the center is what we call the mean or average, and the spread is what we call the standard deviation. In the order scheme of things, an analysis based on where things fall in an ordered list, the center is what we call the median, and the spread, there's different spreads in this scheme of things, but the one we're going to talk about is the interquartile range, IQR. So we'll talk about each of these in turn. I'm going to do this in a somewhat unconventional way. I'm going to start with mean, talk about everything to do with the I'm going to start with mean, flip over to the order scheme of things, and do everything to do with that scheme, and then finish off with back over in the balance scheme of things with standard deviation, because it's the most tedious of the things to compute. So I'm going to do this in Excel. I'm not really going to use Excel. It's just a good place to organize numbers. In fact, just to make a point, I'm going to pop out my calculator. So we're not going to talk about using Excel. I just thought that since I can only have one program at a time open here, it would be a nice way of organizing numbers for our purposes in nice little boxes, I mean. So let's start with the mean or average of a set of numbers. Hopefully this is not a new idea. Add them up, divide by how many there are. What you have to understand, regardless of what you may have heard in the past, is that mean and average are always synonymous. They always mean the same thing. And, well, mean is a little bit more technical sounding. Average is a little bit more common parlance, but they both mean exactly the same thing. This is the notion of the balance point of a set of numbers. We'll talk as we go about exactly what that means. But I mean it in a very literal sense, as we'll see. So the mean or average is the balance point of a set of numbers. Now that's going to have certain consequences, as we'll see. Now the idea of adding up all the numbers and dividing by how many there are is not a complicated one, so the notations may strike you as somewhat overkill. If we're using capital X, one thing you should know for the future is that capital for the concept, lowercase for a specific example of. So if we're talking about the concept of people's heights, then we'll use, say, capital X or capital Y. Call it X. Capital whatever letter you want to use. So if you're talking about the concept of, let's say, people's heights, then we'll use capital X. But if you're talking about a specific person's heights, we'll use lowercase x, and we'll differentiate between them, the first one, the second one, the third one, and so forth and so on. So capital for the concept, lowercase for a specific example. It's nice to have conventions. It's one less thing you have to think about every time. So with that in mind, then x bar, well, lowercase for a specific one. X bar is our notation that we use for the mean or average of a set of numbers. So call the numbers x1, x2, x3, x4. Let n be the number of numbers. So x1, x2, x3, x4 up to the last one, x100, x sub n, whatever. Add them up, divide by how many there are. 20 numbers, x1 plus x2 plus x3 plus x20 divided by 20, and so forth and so on. Now my feeling on notations is that it is better to absorb them before they become necessary than after they become necessary. So the notations here may strike you as a little overkill for the concept of mean, but better now than when we're really going to need it later. So I think the x1 plus x2 plus plus the last one divided by how many you got is pretty self-explanatory. Multiplying by 1 over n, of course, is the same as dividing by n. So this here is an abbreviation for the top. This capital sigma, Greek S for sum. Capital sigma means add up in mathematics means add up every example of. So this is a shorthand for this. The thing about ... is it kind of assumes you see the pattern, and I hope you do. But in future examples, it might be a little cumbersome. So this is a shorthand notation for add up every example of an x from the first one to the nth one, the last one. So this stands in for the numerator, and then divide by n or multiply by 1 over n, which is the same thing. Let's take an example. This is not that complicated, but there's some interesting points to be made about it. So let's take a bunch of numbers here. They can represent whatever you want them to represent, heights of bushes and trees. So 2 feet, 4 feet, 5 feet, 7 feet, 8 feet, 10 feet, 12 feet, 16 feet, 20 feet, 25 feet. How many have I got here? Let's see if I can blow this up a little, because I don't need maybe all of this. Let's see, I'm sure you can see that, but I can't because of the game bar. So let's make it a little smaller. There we go. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. Oh, that's a little too on the nose. Let's make it 11. So let's say 28. If memory serves, you won't be able to see me playing around with this formatting window, but that'll make it look a little nicer. There we go. So there's 11 numbers. Let's double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. So then we'll add them up. I'm just going to do this brute force, right? So on a calculator, 2 plus 4 plus 5 plus 7 plus 8 plus 10 plus 12 plus 16 plus 20 plus 25 plus 28. And for my own peace of mind, I'm going to just temporarily use an Excel function here. A28. Well, that's not right. Oh no, K2. K1, that's what I want. Yeah, 137. That's what I'm getting on the calculator. So they add up to 137, right? So 137 divided by 11. So the mean, add up all the numbers and divide by how many you got. 137 divided by 11 on the calculator is 12.45 repeating. I'm really trying not to use Excel here because I'm not trying to teach you Excel. I'm just trying to have a nice place to organize the numbers, but sure enough, it's 12.45 repeating. So I'll call it 12.5. For no particular reason, for no particular reason, I'll round it to one place after the decimal. As of course, always obey whatever rules of rounding you're given in the problem, but don't overthink it. So 12.5. So what we're saying is that the balance point of these numbers is 12.5. That's the concept of the mean or average. X bar, say that's x1, x2, x3, x4, x5, xn or x11, n is 11. So add them up and divide by n. Add them up and divide by 11. We get about 12.5. So the balance point of the numbers is 12.5. What does that mean? Well, you can think of it in a couple of ways. If you have a very big set of numbers, then you can think of it as the physical balance point of the histogram. So say you've got 100 or say you've got 1,000 numbers and you have added them up and divided by 1,000. Well, then geometrically that corresponds to the spot where the histogram would physically balance. In other words, if this thing were a sheet of metal and we laid it flat, then this line here at whatever we're getting, x bar, is the line where it would balance. Now if it's symmetric, it's pretty clear that that's the line where it's going to balance. But if you have an asymmetric example, then it's a little less obvious. But what we're going for here with the mean, saying for the sake of argument that the mean is this line here, this number on the scale, we're saying that if this thing were a sheet of metal and we laid it flat, then this line, this number on the scale, is where it would balance. So the mean is the concept of balance. You can think of it, for very large sets of data, you can think of it either way, but for very large sets of data, maybe you prefer to think of it as where the histogram as a sheet of metal would balance. For somewhat smaller sets of data, think of them as heavy little weights on the number line. Now the numbers here are different, but we'll come to this example a bit later. So if you put heavy little weights on the number line at 2, 4, 5, 7, 8, 10, 12, 16, 20, 25, 28, then the mean is the line where it would physically balance. Think of them as heavy little marbles at those places on the number line. Then that's another interpretation of what we mean by the balance point. Histogram, sheet of metal, line where it would balance, spot on the number line where it would balance if you put heavy little marbles at those places. So that's the concept of mean. Now I'm going to automate this just to make it a little easier. I'm not going to full-blown automate this because I'm not really trying to teach you how to use statistical functions on Excel. But here we go. So add them up and divide by 11, and that's what we get. Now, what can we say about the concept of balance? Let's flip back over to not the numbers necessarily, but just the visual picture here. If I take this marble here and move it way over here, let's say, to 40, then of course that's going to affect where this thing balances, right? Balance takes into account not just what side of the line things are on, but how far away it is as well. So if I move this marble over here to 40, then it's going to have a pulling effect on the mean. It's going to balance a little bit more to the right than it did. On the other hand, if I take this marble and move it way in here, then it's going to pull the balance this way, right, toward the left. We can see this with the computations. So if I replace that 28 with, let's say, 40, then notice what happens to the mean. It goes up a little, 13. Now the balance point is at 13.5. And there's no limit to this, of course. If I replace it with 100, I can make it 19. If I replace it with 1,000, I can make it 100. Let's go back a bit. 12.5. Now these are not evenly spaced like they would be on a number line. I mean, they're not proportionally spaced, right? 4 and 5 would be closer together than the 2 and the 4. But nevertheless, the balance point would be somewhere here, right? Somewhere between 12 and 16, a little closer to 12, right? So a little bit more than 12. That's where the balance point is. What are we saying? That we've got 1, 2, 3, 4, 5, 6, 7 things on the small side, and 1, 2, 3, 4 things on the big side, right? Because they're not evenly spaced, so you don't necessarily have to have half of them on the small side and half on the big side. What did I do next? 40? So if I make it 40, well, much the same thing. If I make it 100, now the balance point is at 19, right? So I've got 1, 2, 3, 4, 5, 6, 7, 8 things on the small side, and 1, 2, 3 things on the big side. And if I make it 1,000 seems to be a little on the nose, so let's make it 1,100. Now the balance point is at 109, right? Ish, 110. So I've got 10 things on the small side and 1 thing on the big side. Now bear in mind, 100 minus 2 is a lot smaller than 1,100 minus 100. So in the grand scheme of things, I've got 10 numbers relatively I've got 10 numbers relatively close to the mean on the left and one number very far away from the mean on the right. So you see, it's all about balance. Notice also that there is no limit to this principle, right? Well, scientific notation. So 9 followed by 11 zeros, let's say. The mean is on the big side if that last number is 1 followed by 13 zeros, right? Let's turn it back into 28. So what we're saying is that the mean is very sensitive to outliers. Because it's got to do with balance, not just what side of the line things are on, but how far away they are has a pulling effect. Like I said, if I move this marble way over here, it's going to move the purple arrow to the right, right? And same idea over here. If I change this 2, I guess it is, into a negative 16 or something, then it's going to pull the arrow the other way, to the left, right? So balance is affected not just by what side of the arrow, what side of the mean you're on, but how far away it is. So the further away it is, the more of a pulling effect it has. This means that stuff very far away has a pulling effect on the mean. If there's outliers, then the outliers are, like we just saw with the 1,000, let's say. If there's outliers, then it's going to pull the mean in that direction. It doesn't matter which direction it is, right? If I make this very to the left, that is negative 100, let's say, then it's going to drastically pull down the mean. It's still positive 3, but it pulls down the mean. So outliers, long tails, extremities, all of these things have a pulling effect on the mean. The mean is very sensitive to stuff that is far away. And there's no limit to that, right? If I make one number, you could have 1,000 numbers, but if you make one of them 1,000,000,000 times bigger than the rest, then it's going to have a pulling effect. You could make the mean as big as you like by making one number a lot bigger than the others. Or you could make the mean as small as you like by making one number a lot smaller, more negative than the others. So this is not good or bad, it just is. We can make it sound bad. The mean is very affected by outliers. Or you can make it sound good. The mean takes everything about the numbers into account, not just their order, not just where they fall relative to one another. So in other words, any change that I make in this list, no matter how small, is going to change my answer, even if just a little bit. Well, theoretically. Oh, yes, it did. It's a little subtle, but it does affect the mean, right? So the mean takes everything about the numbers into account. Change one number a little bit and it'll change the mean a little bit. Change one number a lot and it'll change the mean a lot. So there's the idea of mean. As for the idea of median, the median has to do not with balance, but with order, where things fall in an ordered list. Now, loosely speaking, the mean is the middle one. Median. Loosely speaking, the median is the middle one. Loosely speaking, the mean is the balance point, and the median is the middle point in the list. This is a little tricky. There is a technical definition of median for mathematical purposes that we don't have to go into. But, well, if you're interested, it's an indefinite article thing. A median is a spot in the list where at least half the numbers are at least that big and at least half the numbers are at least that small. That'll cover the most sarcastic set of numbers you want to think about. But for our purposes, the median of a set of numbers is computed the following way. This is pretty standard from one resource to another. Not so much on Excel. I'm deliberately not going to use the Excel functions here because they're computing things in a slightly different way, but most of the rest of the civilized world computes median in the following way. For the purposes of an elementary statistics course, most books, I think, I've never seen one to the contrary, are pretty consistent on the following rules. Number one, get them in order. Well, I planned ahead. I wrote them in order. But if necessary, you can make a stem plot to get a 20, 30 numbers in order quickly. So number one, get them in order. Everything to do with median and his cousins is got to do with where things fall in an ordered list. So first of all, you've got to order them. Note, by the way, you don't have to do that for mean, right? One of the advantages of mean, the disadvantage of mean being somewhat obvious, we just discussed. One of the advantages of mean is that if you add them up, you're going to get the same thing regardless of what order they're in, right? So there's no particular reason these have to be in order to add them up. The mean doesn't care which one you call x1, and which one you call x2, and which one you call x3, and which one you call x4, and which one you call x5, and so forth and so on. You don't have to order the numbers to compute mean, but you do have to order the numbers to compute median. So the way we compute median is the following. Number one, put the numbers in order if they're not already. Number two, it is the middle one or the average of the middle two. So I've got 11 of these, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You can figure out, or if it's too much for you, just tick them off in pairs on either side. 228, 425, 520, and sooner or later you're going to get to the 1 or 2 in the middle. But if there's 11 of them, then I'll count in 7 either way. 1, 2, 3, 4, 5, 6. Next one. Double check. 1, 2, 3, 4, 5, 6. What happened? 11. Sorry. Can't count. 11 of them, so 5 plus 5 plus 1. So count in 5 either way. 1, 2, 3, 4, 5. This, by the way, is why we double check it. So the next one. 1, 2, 3, 4, 5. That guy. Double check. 1, 2, 3, 4, 5. That guy. So that is the middle one in the ordered list. 11 numbers. The one in the middle is the median. The median is 10. Notice, by the way, what was the mean? 12 something? So this set of numbers is a little asymmetrical, right? The mean is a little bit bigger than the median. Well, you can kind of see it. They're trailing away into big territory a lot quicker over here. These are relatively close together, these not so much. So it's not very symmetrical, but the median is 10. Now, the idea of the median is that it's the idea of the median. For 11 numbers, this is not going to be literally true. But the idea of the median is it's the spot in the list where half the numbers are smaller and half the numbers are bigger. Now, again, there's a lot of caveats on that statement. If you want to be technically precise about it, a median is a spot in the list where at least half are smaller, and at least half are at least that small, and at least half are at least that big. But that's a bit much. So loosely speaking, for large sets of data that are not very sarcastic, loosely speaking, the median is the spot where half the numbers are bigger and half the numbers are smaller. Now for 11, you see the problem. Including 10, not including 10? Not including 10, 5 out of 11 are smaller. That's not really half. Including 10, 6 out of 11 are smaller. That's not really half. Well, guess what? Half of 11 was never going to be a number of things, right? It's not a whole number. So, that being said, one thing I should say about sections 1 and 2 in particular, although we sometimes have to use somewhat smallish sets of data for our examples, the concepts involved in sections 1 and 2 will make much more sense if in the back of your mind you're picturing very large sets of data. You see, it's only the fact that there's 11 numbers that makes this a little suspicious, right? If you had 400-ish numbers, then 200 numbers on the small side, 200 numbers on the big side, it doesn't have to be perfect, you know. If it's 403 numbers, well, you know, it's still about half to either side. So it's only the smallness and the oddness of 11 that makes this a little hazy. But the idea of the median is that it's the spot where half the numbers are bigger and half the numbers are smaller. Again, for 11 numbers, it's not quite going to work, but picture very large sets of numbers. That's when these concepts are meaningful. You can find the median of 11 numbers, but you would probably never need it in the real world. These concepts are more meaningful for large sets of numbers. The other thing that can screw with your perceptions here is having a lot of repeats in the list. Theoretically, they could be 2, 2, 2, 2, 2. Let's do that. Let's make it so many 2s. So there you go. 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. Oops, sorry, 25, 28. Still 11 of them. If they are in order, everything I said, I still mean. Put them in order. 11 blanks. 551. 11 blanks. Blank number 6 is going to be the median. 1, 2, 3, 4, 5. Double check. 1, 2, 3, 4, 5. Well, I wanted 6 actually, right? So again, this is why we double check it. Excel is a pain to lose the color. There we go. So 1, 2, 3, 4, 5, the next one. 1, 2, 3, 4, 5, the next one. So there's the middle one in the list. This particular 2, for what it's worth, is the median. Now again, it's not literally true that half the numbers are smaller and half the numbers are bigger, but that's because of the repeats, right? It is technically true that at least half are no bigger than 2, and at least half are no smaller than 2. So we can play word games all we like. But again, think of very large sets of data with not so many repeats in the list. And you will have a better understanding of what these concepts are. So, okay, so let's highlight it again. That's our median, right? 1, 2, 3, 4, 5. That one, 1, 2, 3, 4, 5. That one. So what if I make this 40? Well, that's still the median, right? That's still number 6 in the ordered list. It doesn't matter what's in the blanks, right? As long as they are in order, blank number 6 of 11 blanks is going to be the median. So whether this is a 40 or a 1000, it's still blank number 6 of 11 ordered blanks. That's 1000. Or, you know, knock yourself out with zeros here. It's still blank number 6 of an ordered list. The median is still of 11 of blanks. The median is still 10. So as you can see, the median is not affected by outliers, extremities, long tails. It's resistant to the effects of outliers, long tails, extremities. The median is the point in the list, loosely speaking, where half the data is smaller, half the data is larger. Again, this is not literally true if you've got 11 numbers, but that's the ideas involved. Let's take a look at our histogram again. What we're talking about visually here. Remember, the heights of the widths of the bars are all the same. It's a standard width. Call it 1 for the sake of argument. The height of the bar represents how many are in that interval, right? So for all practical intents and purposes, the area of the bar represents, whatever that width is times the height. The area of the bar, standard width times how many are there. The area of that bar represents the proportion of data that's between these two numbers, right? So what we're talking about visually here in a histogram when we're talking about median is the halfway area point. The point where you've got half the area to either side, which I'm sure I say somewhere here, down here. So visually speaking, the mean is the balance point of the histogram. Think of it as a sheet of metal. whereas the median is the halfway area point. Now again, if it's symmetric, they're going to be in the same place. This line is the mean because it's where it would balance if you laid it flat. This line is the median because it's the halfway area point. But take something asymmetric and you can see the difference. Take something right skewed, or positively skewed as our book calls it. Take something right skewed, which has got a somewhat longer tail in the one direction than the other, the bigger number direction. These are bigger numbers, remember. Then the median is, the picture is telling us, right here. So this is the line where this is the halfway area point. This is the median. This is the line where you've got half the area to either side. And this, the mean, is the line where it would balance if you laid it flat. Remember, balance is not necessarily when you've got half the stuff on either side. Half the data, half the dots, half the area. Balance, on the contrary, depends on how far away stuff is. So you don't get numbers over here very often, but when you do, they are contributing more than they should by their sheer size, right? I say should, but there's no morality implied here. Again, the median is not better or worse than the mean. It's just very different. It's a very different form of analysis. The mean has to do with where things fall in a balanced list. The mean has to do with the balance point of the numbers. The median has got to do with where they fall in an ordered list. So again, you can make the median sound good, you can make it sound bad. It is resistant to outliers, long tails, extremities. That sounds good. On the other hand, we can make it sound bad. The median does not take everything about the numbers into account, only their relative position in an ordered list, right? So I can change that 28 into a 2800 or a 25.1. Why not 25.01? Or even another 25, of course. And it will not change the fact that 10 is the 6th of 11 numbers in order, right? Now, there's some other points that are a bit more subtle here. Obviously, if I replace this with a 17, then it's going to move things over a bit, but it's still not going to change that this is the 10 is the 6th biggest, right? 6th smallest. So if I make it a 17, then of course it's going to go here, and the 20 and the 25 will move over, but there's still going to be 5 of them on this side, right? So in point of fact, I can change what's in that K-blank there to anything which is at least 10. At least 10. And it's not going to change the fact that this is the median, right? If I make this a 10, then I'll swip it over to here and move the rest over, but this is still going to be, that first 10 is still going to be the 6th of 11 ordered numbers. So the median does not take everything about the numbers into account, only their relative position in an ordered list. Still the median. So there's the difference between mean and median. And we did talk about visually how they stack up. Notice, to bring it back to where we started, if it's symmetric, then anything you call the center, mean or median, should be in the obvious place. But it's when things are not symmetric that there's two competing notions of center that could be theoretically different places. The order scheme of things, where things fall in an ordered list, the halfway area point. The balance scheme of things, where it would balance if I laid it flat, the balance point of the numbers. So there's the concept of mean and median. There are the two notions of centers. Like I said, there are two notions of spread to go along with them. The thing to understand again is that we can either do an analysis on how the numbers balance out, or we can do an analysis on where they fall in an ordered list. Neither is better or worse, but they're different types of analysis. They have different uses, yes, and we'll talk about some of that. But the bottom line is they're very different types of analysis. So if you're using the mean, the balance point, for the center, then the notion of spread that goes along with that is standard deviation. We'll do that or toward the end of the section because it's tedious to compute. In the meantime, let's finish off everything there is to do with the order scheme of things. The notion of spread in the median scheme of things, in the order scheme of things, is the interquartile range, IQR. And that's what we'll talk about next. The order scheme of things has a lot more odds and ends. There isn't that much to say about the balance scheme of things. Nevertheless, the balance scheme of things for the long run, mean and standard deviation, are going to be a lot more important than the stuff to do with median and order, which kind of dead ends in this section. You can see this with the notations. X bar or Y bar or whatever bar is your standard notation for mean. There isn't such a standard notation for median. The closest thing we tend to have is capital M, or if there's any room for doubt, M sub X, M sub Y, if you're comparing two of them, for instance. So there's everything to do with mean and median, and this seems like a good place to stop this video. So part 2 of section 2, part B, whatever, we'll be talking about the rest. I think I'll break it into 3 pieces. Part 2, we'll talk about the rest of the order scheme of things. And then part 3, we'll talk about standard deviation. And then there's some odds and ends maybe we'll throw into that. So part 2 coming up next.